for getting up early, as it appears, and making it down. The important people are here. So I want to talk today about Hadoop, the sort of history, how it came to be, what it's become, and where I think it's going, and in particular focus on one component that's been added to the platform this year, which is search, something that is near to my heart. So first it's worth thinking about how we got here, why we're at a big data conference, what big data is. I think the key thing that's led us here is Moore's Law, that we've had this amazing trend in technology where you can afford to buy more hardware than ever before by a huge margin. We've seen exponential growth for 3 decades maybe now, which is phenomenal. Not something we've seen, I think, in any other technology, this sort of sustained exponential growth. You know, people are often predicting the demise of Moore's Law, and that may come, but it kind of doesn't matter at this point. We've gone through this phenomenal growth, and over this time, a lot of the software technologies have not evolved apace. I think we sort of reached a point, 5 or 10 years ago, where the software technologies weren't scaling well to the available hardware. And around this time is really when big data got started. So first I want to spend a little time defining what I think big data is. Some people hate the term, think it's pure hype. I think it's a term that's here, and it's better to try to embrace it and define it and be relatively clear about what we mean when we say big data. One of the core aspects, I think, is scalability. First, there's the technical part of this. There's the scalable software, distributed algorithms. If you're going to run on hundreds of computers, then you need to worry a lot more about reliability, or even thousands of computers. If you've got one computer and it goes down, once a month or something like that, it crashes, you're not doing too badly. But if you've got 1,000 computers and any of them might crash once a month, then that means several are going to crash a day, and that really means that you have to have systems that can survive the crash of any one component. This is the tricky part about the software, is getting this reliability when you're running distributed. Other aspects of being scalable have to do with affordability. I think affordability is a part of scalability. So in addition to moving things to a distributed platform, we've seen everything move to commodity hardware from exotic hardware. So that with hardware prices about 1/10 the cost on commodity hardware, you can afford to save 10 times the data for the same amount of money and do 10 times the amount of processing for the same amount of money. So that's a huge component here of scalability. The last element of scalability that I think is worth talking about is open source. Open source is a trend that's really accelerated, and I think hit the mainstream with big data around the same time. So it's been very convenient. So a little about open source. Folks in the past were sold software with a license to use it and without receiving the source of the software. And if they build their business around that software, over time the company that's selling the software can raise the prices, or as their business grows, the amount they're going to have to pay for the software might grow because they're going to want to run it on more hardware. And in many cases, this can be a huge cost to companies. And there's also a discontinuity here between the value that a company receives and moreover the cost that it took to produce that software and the cost that it's being sold for. Open source really changes things so that you can get the software for free and then pay for the value that you get on top of the software. And you're no longer locked into paying and renewing some contract which might increase year over year. And I think people have really flocked to it because they're much more comfortable adopting something when they don't have to worry about what it will cost them long term and the unbounded nature of that. In my experience, I started working primarily in open source about, I guess, 13 years ago in 2000 with the Lucene search product. And I've seen that take off like so much faster than it ever would have had it been proprietary software. Had I tried to sell Lucene, I don't think it would have succeeded. I think you would never have heard of it, and it wouldn't be powering places like Twitter, Netflix, lots of LinkedIn, you name it. Wouldn't be doing search that you're running every day. So that's been a huge transition, and also really increases the scalability of things when you don't have to pay for it. It's worth thinking a little bit about different kinds of open source. You've got some systems like, say, Android, where Google writes a lot of open source software and publishes it, but they don't predominantly work as a community in the public. It's really run by Google. Apache has a different style. This is the style that most of the software in the Hadoop ecosystem is developed under, where the software is controlled by a diverse community of people from different institutions. Apache's kind of an odd organization. It's a nonprofit, has over 100 different projects, 120 or 30 at this point, grows every month just about. And each of these is a separate community that develops software. Very few people are paid by Apache. We pay a few system administrators, a part-time PR person, and a part-time sort of administrative assistant. So there's a few people doing some staff jobs, but predominantly all the work is volunteer. So you can't do any of the sort of traditional top-down management where you set a goal and you try to come up with some subsidiary goals and then tell people to go do them, because they're all volunteers. They're going to do what they want. So instead, it's a bottom-up driven organization. All we try to do is mandate how people interact. We have rules for the way that you collaborate in order to form a sort of a level playing field where anyone can contribute to a project. That's the key criteria that makes something Apache in our minds. And so we actually don't have anything, at least from the top, that mandates quality in the software. We don't care from the top-down level of Apache whether the software even works. All that we care about is that some group of people from diverse organizations work together to produce something that they agreed upon. It turns out that if you have these kind of social rules, the communities produce very high-quality software that's very useful. So quality is an emergent thing at Apache. It works surprisingly well. Lots of websites you use are built predominantly on Apache software these days. So back to the definition of big data. The other key component, I think, of the definition, but beyond scalability, is flexibility. And by this, I mean a few things. First, flexibility means that you can take lots of different kinds of data and incorporate it. There's a strategy we call schema on read. It's the common approach in Hadoop-based systems where you load the data in without first spending a lot of time designing a schema for it. Rather, you take it in whatever form it is and keep it that way because that's the authoritative form. And then if you need to have particular projections of it or process in certain ways, then you save those as other data sets because you can usually afford to do that, to store multiple representations. Another aspect of flexibility, perhaps even more important, is having a diverse set of tools that you can use to process the data, to analyze it, to query it. And so we want to have a very general purpose platform with a wide range of tools that are brought to the data. In Hadoop systems, the data tends to sit within Hadoop and the computation, the applications come to it. rather than as often done in more traditional systems with exotic hardware where you might have a storage system and a network that brings the data to the computation, to the database. Rather, we much more want the applications to come together. So we need a flexible general purpose platform that lots of different kinds of computing can be combined on. So some years ago, we started a project called Hadoop based on some papers out of Google. They talked about their file system, a distributed file system at Google called GFS, and we built HDFS modeled after it. And they also described in another paper a system called MapReduce for doing batch processing. And this met a lot of the criteria, sort of, I think, as a big data system. It was certainly scalable, ran on commodity hardware, open source. In terms of the flexibility, though, perhaps a little more challenged. It worked well if what you wanted to do was batch processing, and it was flexible as long as you were able to program in Java, which not everybody is. Still, there was a substantial set of people for whom this was useful, just having this kind of affordable scalability, and it caught on and has grown. So since the beginning, we've seen a lot of tools added on top of Hadoop and around it. So we've got systems like Pig, which is a data flow language for processing data sets. So you don't have to know Java. You've got a much higher level language. Pig on the back end emits MapReduce jobs, so it's still a batch processing engine. Similarly, Hive is an SQL front end that emits MapReduce jobs on the back end. So here you get all the people who know SQL already can now use this technology to process their data. You're giving them this affordable, scalable access to their data. Another project that started is Apache Hadoop, which is a library of machine learning algorithms. So you can do things like suggest people who are like other people, do clustering. There's a whole range of machine learning algorithms in Hadoop. Again, these tend to be based on MapReduce. At the same time, we started to see things that weren't batch-based, weren't based on MapReduce, come into the Hadoop ecosystem. First, there's HBase, modeled after another Google technology, Google's Bigtable, which is an online key value store, often called a NoSQL store. So you can do real-time updates to very, very large data sets and real-time reads of those data sets as well. Last year, Cloudera brought out its Impala open source database system, which is in many ways it's equivalent to Hive. It's got very similar query language and almost identical query language to Hive. It's an SQL dialect. Processes the same sorts of data sets, so data that's living in Hadoop's file system, in Hadoop's native formats. But whereas Hive produces batch MapReduce jobs in the back end, Impala is an interactive SQL engine that can return a lot of queries in a second or two and simple ones in less than a second. So it's orders of magnitude faster than Hive for SQL processing. So we're starting to see a wider range of tools being added to this platform, really seeing the flexibility borne out in that you don't have to be a Java programmer, nor do you have to be building a batch-based system. We're starting to see most of the major different kinds of processing that people do on data supported by Hadoop. One thing that was missing a year ago was a good implementation of search that really integrated with Hadoop. So we set about at Cloudera to add one. Actually, I'm going to first observe that what we're really seeing Hadoop become is an operating system for big data. It has all the characteristics that I think define an operating system. It provides a common set of APIs for applications to build on that manage resources for those applications. So controls the access to the disks and to files and to memory and to the network, and coordinates all of that and manages security issues and so on. And I think there isn't another contender out there for a big data operating system. Hadoop really seems to have taken that role. And it means, I think, that if you're building a big data application and you want it to integrate well, you want it to be able to operate on data without moving it, operating on it in place, then this is the platform that you want to migrate to, that you want to be native within. So again, we wanted to add search to this operating system. Why search? Search is incredibly useful. Most of us search on Google every day. We search within our email. We search in lots of different applications. So it's a metaphor that we all are used to and know how to use. I remember working on search engines at Excite in the 90s and watching over the course of the 90s how much more sophisticated people's queries got. We as a society have learned how to use search engines, learn what are good query terms, learned how to refine our queries based on what we see in the result set. It's a skill that we all have. And so taking advantage of that skill in big data is very valuable. It lets you, there's a lot more people know how to do search than know how to use SQL or can program in Java. So it really can open up data sets to a much wider community. So if we're going to add search to Hadoop, how should we do this? And as I indicated earlier, that what we really need to do is make it native. We need to make it live within Hadoop rather than as a parallel system. So a year ago there were other distributed scalable search solutions, but they really stored everything outside of Hadoop and existed as a separate parallel system. Rather, we want something where we can share the storage, obviously, reasonably. We also like to be able to share other resources, CPU, memory. We'd like to be able to share things like authentication and authorization, systems like disaster recovery. As much as possible, we want to share these aspects of the platform, which are just common needs that can be provided at the OS level here. So we went about and we looked for what were the right tools and ways to do this. And we ended up incorporating Apache Solar. I don't know who here is familiar with Solar? Number of you, all right. So Solar is a library built on top around Lucene, which packages Lucene as a web service. So you can query it over the wire. Over the last 3 or 4 years, a team of people has worked to make Solar be scalable and distributed. And that work was first available really in a stable form a year or so ago. And really opened up Solar as a possible platform for this, but it really, again, was one of these systems on the side. Wasn't integrated into Hadoop at all. And so we looked at how to do this, and the answer we came up with was to first store indexes in HDFS. I'm going to talk about that next, because that was sort of the interesting challenge that had, I think, kept people away from integrating search systems into Hadoop before. So that was sort of the nut to crack. But additionally, we added a lot of integration at other points. So there's the Hadoop user interface, where we added an ability to search in Solar from there very easily, and to build search interfaces that way. We added some tools to make it very simple to do indexing from MapReduce, to have events from Flume. Say if you've got log files that you're on your front-end servers that you want to automatically be searchable as events are happening. You want the events to be searchable within seconds, so we can integrate that through Flume. Also, as you update entries in HBase tables, you'd like to have the entire HBase table be searchable. So I'm going to go through each of these in a little more detail and talk about what was required to get these all to work well with Solar. First, putting the index on HDFS. Many years ago, before it was even called Hadoop, the Hadoop technology came out of a project called Nutch, and we tried putting Lucene indexes into HDFS, was then called NDFS, and it worked, but it was horribly slow. And if you ask anybody, as of a year ago, why don't you put your search indexes in HDFS? They say, we tried it, it's really slow. And so, fortunately, somebody questioned that and went and looked at why that was the case. A fellow named Aaron McCurry, working on a project called Blur, which is also at Apache. And he realized the reason why search was so slow running on HDFS was that HDFS doesn't have any sort of a client-side cache of the file system data. When you're using a Unix file system or a Windows file system, there's data that's cached by the operating system so that if you attempt to read the same data that you've read recently, it doesn't actually have to read it from the disk. And Lucene had been built, Lucene and Solar, built for years and optimized based on that assumption, because they were always talking to files that were on the local disks. HDFS worked differently. For the initial applications, batch processing, those sorts of caches weren't useful, and they weren't built. But if you add a cache in, all of a sudden you've got a search system which performs with its indexes in a distributed file system as well as it does with them in a local file system. So that was a great discovery by Aaron, so we borrowed his methods of caching the HDFS I/O a bit, and we're able to pretty easily really bring search into the Hadoop space by getting indexes stored in HDFS. And there's lots of advantages to this. You no longer have to worry about managing separate spaces on drives if you're going to share a machine, managing separate machines, and that you can really pull it into the same ecosystem. So some of the ways you can index documents are first MapReduce. If you just want to, if you have a big set of documents and you want to create an index for them, you can do that easily with MapReduce. We've provided some library code to make that very simple so that each reduce task will create an index shard, and then you can launch your search system running on those indexes. Some people use this who, the first time they create an index, some people end up recreating indexes on a regular basis, say nightly. They have some aspects of their indexing which are based on big batch computations. Let's say you're doing some sort of graph analysis like PageRank, and you want to incorporate that into your search engine. Oftentimes that's hard to do incrementally, and so you do a batch and you do batch reindexing. So that's the first level of integration that we added here. Then we added another one where you can use MapReduce to do indexing, but you can use it to update a live index. So you can run a big batch process, build new indexes, and then tell a live search system, take these new indexes and integrate them atomically into your results. So that's sort of a hybrid batch and online approach. Then for actual real-time events, we added a Flume agent that can, or a Flume sync, sorry, that will index documents as they come in. So you've got log files, or what Flume commonly collects events from, and Flume will reliably route logging events into other systems like HDFS and now Solar, so that within seconds of some event happening on a web server, it's logged, and that log entry is indexed, and folks can search on it. This is lots of applications. People use this so they can very quickly see who's done what. They can help diagnose problems. They can do reporting. Anyway, we can go through some of these applications in a bit. Another point of integration is HBase. So here, as you're adding and removing entries from HBase, you can update a Solar index. We worked with folks from a company called NG Data to add this. It works sort of asynchronously from the updates in HBase. It doesn't slow down your HBase performance at all. It hooks in at a mechanism in HBase for doing mirroring, so that we get every change that happens in HBase and can send it into a Solar index. Another tool that we added was a thing we call morph lines. This is a library that when you're building search applications, you end up writing, we have these general purpose tools, like the ones I've described, to do indexing, but there's some specifics of each application. If you've got log entries and you want to index the IP address and the the URL and various things. You want to index them under particular fields using some particular schema in your Solr index, but you need to map the two together, the events from the log to the schema that you're using to index them. And it takes not a lot of code, but a little bit of code. And so Morphline really attacks this problem and makes it so you can just configure as a series of processing steps. You can configure a pipeline of processing steps to take incoming data and convert it into a form that's appropriate for indexing. So it just makes it simpler to do this boilerplate code, lets you then build a library of pipelines and pipeline components that you can call upon, and they entirely live within config files, so they're easy to store and operate with. They're sort of part of the cluster configuration. It's a pretty neat system. You can put conditional logic in the config files, bits of code if you need to, and then it helps you glue these things together. So as an example, if you've got a system that's generating logs, you've got the Solr sync that's receiving these events, then you can use a quick pipeline of 3 to read lines from the log file, match some regular expression against them, pulling out various fields, and then index those fields. You can look on there's a lot of great documentation for Morphlines, a lot of examples of what this ends up looking like in the config file. But trust me, it saves you writing the same little bits of code over and over to integrate things together. Another element I mentioned was Hue, building search interfaces within Hadoop. Hue is the Hadoop user experience project. And this is an example, you probably can't see it very well, but this is from a frame from a video. It's, you can search for Hue search. I think that'll find it for you. Search in Hue or something like that. You'll find this video where they start with just doing the basic raw search with no customization whatsoever of an index of the Twitter Firehose feed, and then in a series of steps interactively refine this search interface so that we can pick out the icon of the poster, of whoever posted the tweet. We can highlight the matching query terms in the search results. We can add a link back to the tweet itself. These are all things picked out of the result set and added into the HTML. And it's very simple, very simple interactive way to build a pretty highly functional search website without having to do a lot of code again. This is all sort of configuration done in Hue. On the left, you've got the facets. For those who aren't familiar with Solr, Solr will automatically facet your searches based on the result set into categories, and then you can choose among those. And getting those displayed is, again, very simple to do with this Hue tool. So summing up on what this search tool integrates, you can have events from Flume flowing into Solr. You can have events from HBase, every change in a table flowing into Solr. You can do MapReduce jobs to do bulk updates or create indexes entirely. If you've got a great big index and you want to create it the most efficient way possible, then you do that as a big MapReduce batch job. On the search side, you can use the Hue system to build a very simple to build interface for search. You can use the standard Solr APIs to build some sort of custom interface, or use some application that you have that integrates search already that talks to Solr. So it's a pretty widespread integration. We'll probably add more to this. It's all open source. As much as possible, we've tried to push whatever bits of code have been developed back up into the corresponding projects that exist. So the index is living on HDFS. That code to store indexes in HDFS has already been pushed back up into the Solr project. The stuff for Flume has been pushed into the Flume project. and so on. We're not trying to build a new project so much here as help a bunch of projects be better integrated to search enable the Hadoop ecosystem. If you're Cloudera has a product called the Cloudera Manager, which is not open source for managing clusters, does deployment, configuration, monitoring, and so on of services within the Hadoop ecosystem. Search is now supported there, so you can deploy search and you have a very simple interface to decide how much CPU and how much memory and so on you want to give to search versus other components in the ecosystem. So I encourage you to check that out. So it's Cloudera Manager is a free download. It's not you don't have to buy the software, but it isn't open source. I want to characterize some use cases here for search to sort of close up and on how this is useful. First one is sort of what I alluded to, which is it brings this platform to a much wider range of users. There's people who weren't able to effectively use SQL or Java or whatever other system you had to access data in Hadoop can use search engines. So that's a huge advantage. And we're seeing a lot of places adopt this search in the platform for this reason. So, example here is insurance claims agents, nurses, doctors, people like that who want to directly be able to look through data in Hadoop are now easy to support. These other cases are sort of more general things, advantages of this platform approach. So we're supporting lots of different uses of the same data. So if you have log data coming in, you can do your nightly reporting and every day see what pages people were clicking on the most, what advertisers were generating the most revenue, and have all these metrics that you might produce. But also, if something goes wrong, you might want to have your technical people be able to search through and backtrace and find what happened at some particular point in time and correlate various events. And search is very handy for that, to do this sort of browsing through the logs interactively rather than the batch reporting. So it's a complement. It's a new sort of processing that you can do over data that you already have in Hadoop. And the third class of use case I want to talk about is this notion of, again, a general principle of the platform is that you can bring data sets together from multiple parts of an organization, data sets that used to be in silos and you couldn't easily work together. And now you can integrate those. And search is another tool you can bring to those. So you can have different data sets that you put in a single index and search together, and have open these data sets to a much wider use than they were previously. A lot of times you have an in-house system that's built, and it's built for a particular, to satisfy a particular part of the company. As inventory management might only be used by the people who manage the inventory, but it might be of interest to lots of other parts of an organization. And if you can get that data out and into a general purpose system and combine it with other data within an organization, then you can get a lot more value from the data. And search helps to bring that about because it gives you one more tool in the quiver. So that's all I really wanted to talk about. I wanted to let you know that search is now available as a part of the platform, tell you a little of the story of how and why we added search to the Hadoop platform. Encourage you to have a look at it. It's just going to be a base part of Cloudera's bundling of the Hadoop ecosystem, CDH, that anybody can use. Currently, it's a separate download, but starting pretty soon with CDH 5, the next major release, it'll just be included in as a standard component. I think we've got some time for questions. Yeah, we've got lots of time. I'm ahead of schedule here. So if anybody has any questions about Hadoop, search, Lucene, or anything else, Apache, I'm happy to handle them. Don't be shy. I answered all of your questions? There we go. We got a brave soul. She's got a mic here for you.
So I missed the earlier part of the talk. You were saying you could search, do free text search on top of Hadoop. So, for example, if I have a number of files in HDFS and I just want to search for, a phrase, that use case is supported now?
Well, you have to have some. You have to explicitly index. We're not automatically indexing every file in HDFS. So if you've got data that's in HDFS already, you'd probably write a MapReduce job to index it and decide what aspects of it you wanted to be searchable. Does that make sense? So Lucene does, the sorts of search that you're used to doing at places like, Netflix. What's the shoe place? Zappos. The Amazon, that style of search, if that sort of seems like the sort of thing that you could specify for your data, then you need to tell it what are the fields that describe this and then load the data in to the index. Does that make sense?
Right. So, and the data could be in HBase or HDFS both.
Yes. Yes.
So,
yep. In either case, you need to do some configuration. In the case of HBase, to get it to have all of the entries indexed. If you've got things that are just flat files in HDFS, then you've got to run a MapReduce job to get them indexed. Unless you're indexing events as they arrive with Flume, at some point you need to explicitly say how you want them indexed, as you would.
And which works better? If the data is in HBase, works better than HDFS? Like faster search?
I think they both. It doesn't affect the search performance where the data comes from, because the searches only look at the indexes. They're not going back to the original data to do the searching. So it doesn't matter where the data comes from for search performance.
Thank you.
Yep.
I have a question regarding your caching technology. I think this is very applicable to our things. We see lots of GC pressure when we do batch indexing. We're currently not using Hadoop we're just using a very traditional way of doing batch indexing for our Solar. So by adding that caching layer, do you see pressure when we are doing like mass indexing?
Do we see pressure on memory when we're doing indexing?
On memory, because Solar is a Java application. Is the caching in the Java heap or is off the heap?
It's off heap caching. Yeah, so it shouldn't affect GC in the processes. Oh, there's somebody over there. I don't know. We'll get to you.
So you mentioned that you can index directly out of HBase, and you can do live stream event indexing through Flume. What other tools are supported? For example, if we have a Kafka queue, are we able to index directly off the queue, and are we able to index from like Cassandra, for example?
We haven't added support for explicitly for Kafka or other tools. It shouldn't be hard to take the Morphlines library and use it directly, because it's really Morphlines is the tool that the Flume sync that's been added is a pretty thin amount of code. With the most of the interesting code is in the Morphlines. So writing the equivalent of I don't know what they call a sync in Kafka that would then call Morphlines and use that as a library to do the indexing shouldn't be much work. We haven't done that yet. We're hoping that more people will start integrating more components like Kafka.
To what degree will the efforts of Apache Foundation and the companies that Cloudera have now clustered around it do in creating maybe an alternate form of commercial data center, a second tier or a third tier data center provider? These tools that can obviously be used in a private cloud and in the public cloud, will they act as a catalyst for new types of commercial data center operations that are underdogs to go up against the big guys?
You know, I don't know. is the short answer. I mean, I think we're seeing a lot of opportunity for disruption in the software market. In cloud, public cloud, it seems like we've got some pretty big players. I don't know that that's going to be disrupted anytime soon, but it's not an area that I have any real insight into.
A silly question. I mean, so you chose Solar. Is there any reason? Did you look at Elasticsearch?
Sorry.
I'm sorry. Did you look at Elasticsearch? And why did you choose Solar over that? And would it be hard to actually take what you did for Solar and actually adapt it?
We did look at Elasticsearch. We chose to use Solar for a couple of reasons. One was Solar's more mature. It's got a lot more tools integrated with it already. It's got a lot more features than Elasticsearch. We like Elasticsearch. I think it's a great tool. It's in its favor, it's a little more lean and mean than Solar because it's younger. I think the deal breaker was really that we wanted to use a technology where we could easily integrate changes upstream and get people who were peers on the project. And Elasticsearch is controlled by a private company that is not interested in developing it at Apache. They want to maintain that control, and we thought that was not something that we wanted to build such a central component of the platform around, dependent on the blessings of that company. Rather, we'd rather depend on our peers at Apache to manage the technology. So that was the big, they looked pros and cons technically. So it was more of a political issue. That's it? All right. Thank you very much.